Okay, this is where I left off last time. Just to tell you what empirical formula is, when it comes to ionic compounds, I thought we had lab scheduled today, but it's not on our schedule, so we'll do that next week. Didn't I say we had lab today, last time? I came in this morning and realized we didn't, so I'll let you know. We're not even set up in here to do lab, the next lab. If it's an ionic compound, like that is already so the formulas we come up for ionic compounds are already empirical. They're designed just to be like that. But for molecules, for molecular compounds, should I go through all this math? I guess I could. So I could say, if I just said C2H4, what is percent carbon and what is the percent hydrogen? So we would start by going carbon, there's 2 of them. Hydrogen, there's 4 of them. Carbon is 12.01 off the periodic table. Hydrogen is 1.01. We get 24.24. Times 2, 24, 2. This would be 4.04. or grams per mole, or AMU, but we're going to use grams per mole. So that's the total of what that weighs in grams per mole. So if that's the total, we have 24.02 of carbon over 28.06 times 100. .02 divided by 28.06 times 100. I'll keep 4 digits here. So that molecule, and that's the structure of it. I haven't talked about double bonds yet. I'll get to that soon. But that particular molecule is 85.60% carbon, hydrogen. Should put a percent sign here because that's where the unit comes from. 4.04 divided by 28.06 times 100. Now let's go to C2H6. Let's do C4H8. For the 0.04 grams per mole, 8.08, 56.12 grams per mole. So 48.04 over 56.12 times 100 for carbon. Hydrogen. .08 divided by 56.12. 85.60, 85.60, 14.40, 14.4. And that would continue for all of these. That's one way to say what empirical formula means. And maybe it was obvious it was going to come out like that because I'm just scaling up by 2 each time. 2 and 4, multiply them both by 2, you get 4 and 8. Multiply those by 2, you get 6 and 12, and so on. These are the structures. Let me put it like this. Molecular formula C2H4, C4H8, C6H12, C8H16. And I could continue. In some sense, that's infinite. So C2H4, there's the structure. Its empirical formula is C2H4. C4H8, its empirical formula is C2H4. The empirical formula of this one is also C2H4. The empirical formula of this one C2H4. Say again? Well, you're kind of looking right at it. It's kind of like, I could say the percent of each constituent in there is the same as it is. This one is, I erased it, what was it? This was 14, I made this 80, what was it, 86? So this is 86% carbon and 14% hydrogen. This is 86% carbon and 14% hydrogen. This is 86% carbon and 14% hydrogen. So they're kind of a family of molecules who, the empirical formula is this, and I think I said last time that it's kind of an antiquated idea really, because there was a time when you would take an organic compound like this, put it through a combustion analysis, find out how many grams of this you got, how many grams of this you got versus your original amount of grams from your sample that you combusted, and then you could find out percent carbon and percent hydrogen. And the point is, if you put this through that process, you'll get 84% carbon and 14% hydrogen. For this, you'll get 84% carbon and 86% carbon, 14% hydrogen. And the point is, you can't identify the molecule by that combustion analysis, but you can identify that it is in this family of molecules, which was useful back in the day when we didn't have all the fancy techniques we have now. So this concept kind of survives in the textbooks, and the idea of an empirical formula survives in the textbooks because of that, but it is kind of antiquated. But you can find the empirical formula of something if you do the combustion analysis. In a combustion analysis, the results are either, you can either say, here's the gram sample I started with, and here's the grams of the things, or you can just go straight to and report it as percent. But you can still find out what the empirical formula is for a compound. So I'll show you how to do that. So I'm just going to finish up what I had on the slides last time and show you how you find the empirical formula. And then I'll go on to something new. All right, I didn't print this out, I should have. So that's the idea of an empirical formula. Find the empirical formula. This is that many grams of iron and this many grams of oxygen. Okay, that's what this problem says. It says, I've got this sample and it's this percent iron and this percent oxygen. It doesn't say any more than that. So here's what you do. You know that it's, so the positive one goes first and the negative goes last. It's the same as saying the metal goes first and the non-metal goes next. And then it's like, what is that? What is the empirical formula of the sample? You could probably tell me already. Well, you might be able to tell me. It's either iron 2 oxide or iron 3 oxide. It won't be anything else. But pretending we couldn't figure out close to what that formula is, you would do this. Do you have your periodic table from last time? Okay, tell me what it is for the grams per mole for iron. 35? 85. And oxygen is 16. So here's what you would do. You find out how many moles there are with each one of these. I have that many grams. I'm going to put grams of Fe down here because it needs to go away. Moles of that to be up here because I'm going to need to end up in moles of Fe. 1 mole is grams. Okay. 34.97 divided by 55.85. So we've got 4 digits there, so I'll go 6261 moles. Oxygen, I have 15.03 grams of oxygen. Grams of oxygen, moles of oxygen, so that I'll end up on moles of oxygen. 1 mole is 16.00. Now that we have this in moles, the way I do this, I go ahead and stick them in here. So here's what I've done. I've got Fe 0.6261, oxygen 0.9394. So we need to turn that into whole numbers. The easiest way to start when you do this is take the smallest number that's there and divide everything by that. Meaning I'm going to divide 0.6261 by 6261, which is going to make this Fe1. Now I'm going to divide this larger number by 6261. 0.9394 divided by 0.6261. And 1.5. This one's going to come out to be perfect 1. This one will come out with something and a bunch of change just because of experimental error. But it's essentially 1.5. I mean, there's at least zeros here, so I can truncate that to 4 anyway. That 3 wouldn't round that. So I'll stop there. And let me just get these zeros out of our way. We're trying to get to whole numbers. So what can I multiply through by it to make this the smallest whole number it could possibly be? 2. I'm going to multiply both of them by 2, which gives me this times 2 is that, this times 2 is 3. That's the empirical formula. Because this is an ionic compound, I'm not going to say this, but you could, I'm not going to, this is kind of silly, but notice, it really doesn't make sense with ionic compounds, but I'm saying this empirical formula means it could be this in my sample based on this analysis, but I might have had multiply everything up by 2. It might have been that, or I might have actually started with 2 times 3 is 6, times 2 times 3 is 6, 3 times 3 is 9, 2 times 4 is 8, 3 times 4 is 12. So really there's a family of compounds that's like this, and what this analysis tells me is I've got one of these. But that really doesn't make sense with ionic compounds. The example here did an ionic compound. But that's how you find empirical formula. If I put any up like this on D2L, I'm going to do them as molecular compounds. I ended up with this many moles of iron, so I put it there. I ended up with this many moles of oxygen, so I'll put it there. And then you take the lowest number you've got, and you might have more of these, but you find the lowest number, because there's not necessarily only 2 things. It might be C2H5O and 3 or something like that. But you look at all of those numbers you've got, and you divide them all by the lowest number. So I divided this by 0.6261, and I divided this by 0.6261. And that's where those numbers came from. And this, of course, is going to be 1, and then you get weird fraction stuff with everything else. But you're trying to get them all to be whole numbers. So if you don't land on whole numbers here, you think about what you can multiply everything by so that everything will come out to be a whole number. I'll dig up more examples of that. Maybe I should do one that's a good one in the book. It's kind of silly for, the concept itself is a little odd for ionic compounds. let's look at the end of the chapter and see if there's a science, chemistry. Two. Let's do chapter 37b. This one gives you, it says, carbon is, this one's a little different than the way I did that first one, because they're giving us percentage. I just think there's the wrong one all of a sudden. 53.3. What is the empirical formula? That's what we're asking right here. Okay, those should add up to 100. That's 1, 7, 8, 9, 10. Add to 101. Yeah, that adds to 100. Okay, first, if you give it in percent, first, assume you have 1 mole of C something, H something, O something. If you do that, then you can go, if it's 40%, so 40% of 1 mole is 0.40 moles of carbon, 0.06 mole of hydrogen, and 0.5 mole of oxygen. So those all add up to 1 mole. Now we're going to go this here. Okay, what's the lowest number there? This is the smallest number, so let's divide everything by H1. This divided by 0.0670, 0.533 divided by 0.670. Oh, I have 7.95522. This divided by 0.0670. This becomes so this is so close to 8 and this is so close to 6 that I would just go ahead and round it and say it's C6 H1 and that's the empirical. It's an odd molecule. $46.7